It is so interesting because you're so right. As we move from compiled to interpreted languages to scripting and then, software development in the cloud, people got more and more disconnected from hardware reality. And it's been amazing to me because I'll have conversations. I just met a bunch of software vendors this week and explaining to them, move the data, store the data, process the data. And this works at inside the package SoC level. It works on the motherboard. It works in your PC.
Yeah.
Works in the data center, rack node, whatever. It's kind of all the same principles. You might use different terminology for the I/O, but you don't want to stall the pipeline, whatever you're talking about.
I mean, we have on a routine basis, we're running applications. I mean, these are live production systems for customers that are running on Intel NUC clones, right? These are little, 4-inch by 4-inch box. They've usually got an i9 processor in it, and they will do more work than an entire cluster of servers in a data center. And all we're doing, and that's not hyperbole. I mean, that is literally what's happening. And all we're doing is we're asking the CPU to do an honest day's work each day instead of doing a day's worth of work, sleeping for a century, and then waking back up to do one day's worth of work. And again, when you say it that way, it sounds stupidly simple, but boy, does it have an impact.
Yeah. So is this, I know that you've talked about this innovation around locality optimization.
Yeah.
Is that a piece of this? And maybe go into it a little bit more technical for our technical leaders that are listening.
Yeah, no, that's exactly what it is. If you look at the heart of what we're doing, it's all about locality of optimization, both locality of reference in terms of the data that you're referencing, and also locality of compute. Because our whole goal, so for the folks that are more technically oriented, think about your textbook back in college on optimizing compiler design. Take all of those concepts, and those have been around for decades, on how do you move decisions from runtime to compile time, right? Because that's the whole point. You want to figure out a bunch of things ahead of time. You want to cheat, right? Instead of figuring out things while the program is running, figure out as much as you can at compile time. Do the work at compile time, and then at runtime, when your program's running, it's super fast. We're doing exactly the same thing in a distributed processing environment. So the moral equivalent of compile time is system generation time. You're going to spin up this network of distributed processing nodes. And so the question becomes, what data physically gets placed in each node, and how are you accessing the data? And the computational payloads themselves, the programs, how are you getting them out to each processor so that at runtime, you've got the code locally, you've got the data locally, and you're keeping that CPU core busy. And if you can do that, the really cool thing about Fractal is you can do it at scale, right? Because if it works for one node, it works for 10, 100, 1,000,000. We've got a theoretical limit. It's a ridiculous number. It's 2 to the 64 to the 2 to the 64th fractal instances. We run out of address space. That's that's a number that's ridiculously larger than the number of computers that have ever been built and will likely ever be built in mankind's existence. So scalability is pretty good.
Well, your numbers are astonishing. Just for the people that are listening, it's 100x faster performance, 90% less infrastructure cost, all while eliminating corruption risk. And most people assume that you have to choose between safety and speed. How does the fractal architecture deliver all of that at the same time?
So it's interesting. With this approach, what it does is it enables you to use speed to get you safety. Because you're right. Normally, to make things safe, if you look at trying to put safety into an existing system of record, an existing enterprise application, you're usually doing it with guardrails, right? So you think about trying to add, AI capabilities, particularly AI agentic capabilities, to an existing enterprise application, and you're putting in a bajillion safety checks everywhere you can possibly put a safety check, right? So massive overhead, massive computational cost. And you can make it safe, but you take a system that frankly was probably already slow to start with, and you make it agonizingly slow. Well, with a distributed processing approach, you get to use speed to your advantage because when we transform an application and run it in this distributed processing mesh, the practical real world speed up that we'll see is anywhere from a factor of 100 on the low end to on the high end. We actually have a couple customers running 1,000,000 times faster. Now, that's admittedly an egregious example. That the average
Right.
customer is not going to see that, but it's multiple decimal orders of magnitude. Okay, that's great. What can you do with that? Well, what you can do is you can say, this thing's so gosh darn fast, it actually makes sense to run a completely parallel system to my system of record, continuously import data from that system of record, do all of my work here, do my safety checks here because it's so blindingly fast. And then when I get to checkpoints that make sense, export that data, back into the system of record in a very controllable, monitored fashion. So you're using just raw blinding speed to give you the chance at safety. Because if you were to build the parallel system, if you literally did it just as a parallel system, if you just duplicated the original system, it won't run fast enough. There's no way it'll run fast enough. So you can use speed to get you safety. If it's fast enough, it's got to be really, really fast.
Yeah. So I'd love it if you could share any real world example, whether it's utilities or telecom. Do you have a Fortune 500 customer that has deployed the digital twin and seen these kind of results?
Oh yeah. Let me leave their name out of it because I don't have permission to use their name in a public setting. But there's a company where one of the core things that they do is billing. They generate a lot of bills, and they do it the same way. A lot of companies where a big corporate of their operation is billing, they take their customer base and they break it into segments. And this particular client takes their really big customer base and they break it into 24 different segments. And so if you look at the typical month of how this company operates, they wake up on the first of the month and they generate bills for 1/24th of their customer base. They do the same thing on day two. Get to the end of the month and they've got kind of a week to basically clean up any problems that they had, resolve disputes, issues, what have you, and then do the same thing again the next month. They run that application in a custom-built $85 million data center that they are very proud of. You'd love it. It's very clean. It's very shiny. They've got chrome guardrails inside it. I mean, it looks like something out of a movie set. It's very. Okay. We're doing the same operation in parallel, and in fact, it's an interesting use case because we're not their billing system of record. What we're doing is we're running in parallel with their billing system of record. We take the output of our system, we take the output of their actual billing system, we reconcile every bill down to individual line item detail. If both systems agree, that bill is correct. If they don't agree, then you need to resolve what the issue is. And so far, knock on wood, we're actually batting 100% perfect batting record. When there's been a disagreement, our system's been right, the legacy system's been wrong. Now, at some point, I'm not going to be able to make that claim anymore, but as of today, I can still make that claim. But anyway, doing that operation, if you look at the actual system of record, they lock the data center down for 4 hours a day for 24 days out of the month. That's what it takes to generate all the bills.
Wow.
We do the same thing on 3 Intel NUC clones, and it takes a little under 4 minutes. It's like 3 minutes and 47 seconds.
I love that. I love that.
Yeah. Spectacular difference. Yeah. Right. So, and that's a real world production example. Yeah. And again, if you step back and think about it, okay, it sounds impressive, but it's actually not surprising because what's going on in that data center is, you walk in and it's beautiful. You've got all these servers and the lights are blinking and you can hear the fans screaming. But what are they doing? They're working for a day. They're going to sleep for 100 years. They're working for a day. They're going to sleep for 100 years. Most of the time, they're just sitting there. Those 3 little Intel NUCs, we're keeping them busy. I mean, they are warm to the touch. They are very busy, but they do the same job in a couple minutes.
That's amazing. So I would love your perspective, Michael, on how this translates with AI. So I have an AI governance professional certification. And when I studied for that, governance and human in the loop were a chatbot interface, right?
Yeah.
And you could afford the policies and the committees and everything else. Well, unfortunately or fortunately, we want to have AI act autonomously.
Yeah.
But we also need to maintain control over what gets written back to production
Yep,
systems.
absolutely.
So how does your controlled promotion process help solve that tension of you put autonomous AI and agents to run faster, but then you put humans in the loop and you can't run faster? So we'll love your view.
Yeah. So the trick is to you've got to make the interaction points human digestible. So if you look at AI, the thing that captures the news and that people are enamored with because it just seems so amazing is super general purpose AI, right? Where you can ask it anything, it does anything. Really freaking hard to control, because if you actually are allowing it to do anything, good luck figuring out what the guardrails can possibly
Right.
be. And it's attention grabbing and it's super interesting technical work, but no one has that. Well, very, very, very few people actually have that business problem or business need, right? And I think what's happening is AI is moving from kind of the sex and sizzle to the I want to do practical things with it, right? I want to solve practical business problems. And so once you're actually trying to do something practical with it, our experience has been most of the time what you really need are much smaller agents doing much more constrained tasks, right? If I'm building an agent to help my call center people, it doesn't need to know how to quote Shakespeare. It just needs to know everything about the product they're trying to support. It is a fantastically more constrained problem. And so, interestingly enough, our fractal architecture seems to fit really well into an agentic world, because what we do in our fractal deployments is a fractal instance will have a single agent with specialized knowledge deployed into it that's doing a particular task. It's a lot of times you're mirroring what you see in the physical world, right? If you look at an organization, how does an organization work? Every employee doesn't do every possible thing that the company could do. They have specialized tasks, right? They tend to have a fairly focused role and set of responsibilities and data that they touch. And if you do the same thing with your AI agents, it makes it digestible. A human can actually understand it. I need to make sure this agent touching these particular data sets, doing these particular tasks, hasn't done something wonky. That's usually not that hard, right? And so instead of making it this incredibly difficult problem, break it down into 100 different problems where each is bite-sized, kind of digestible, get them working one at a time, and there you go, right? Again, it's the beauty of a distributed processing approach. If your core foundational architecture is a distributed processing mesh to start with, a lot of things that right now look hard wind up becoming not hard because they very naturally decompose into these bite-sized things. And once it's something that a human can look at, they can kind of load the whole problem into their head. It's not that hard. It's a solvable, practical problem.